veloce.
We should wait for a bit more people to come in the room again. Sound check, sound check. 1, 2. Hey, here you go. Andrei is coming. Maybe Carlo at some point will show up as well. Andrei, would you know if Carlo is anywhere close to the door? Never mind, never mind. So I don't want to steal your thunder. Just want to greet everybody. Apologies, this morning was a bit late. Not everybody knows me. I'm Giuseppe Correale. I've been working in the team of science, supporting several experiments on ISS for a while. and I want to make sure that everybody knows Monsieur Brice Saint-Michel, who is my successor. I think many people are involved in the experiments are already aware of him. I wanted to also talk to Carlo about the FDT meeting that was supposed to happen. It is supposed to happen between this afternoon and tomorrow morning, but I'm not sure about the logistics of it. So Carlo, we'll wait for him to pop up and decide what to do. And about the social dinner that we had that we have planned for tonight for those who are invited from the speakers. I'm gonna send an email to reiterate the address, and I have high expectations for a nice evening with everybody. So I leave the floor to you. Thank you. And maybe when maybe when Carlo is back, we can try to talk about the FDT meeting. Oh, thank you. About the FDT meeting. So the presentation for the FDT, which stands for Facility Definition Team, for whoever is not familiar with the term, has been moved to 2 o'clock in break room one. And I think we will follow the presentation. Maybe after that you can have the meeting, and the meeting could start also as a team huddle in the coffee break room, region, zone, whatever you want to call it. So again, we'll wait for Carlo for further instructions on that. Thank you.
Thank you, Pepe. So welcome back, recharged after the coffee break. And I'm glad to present the next speaker, which is Senthil Kumar Parimalanathan from Transfer Interfaces and Processes Laboratory at Université Libre de Bruxelles. So can you upload the presentation, please? And no, you can. Okay, there is that one too. No.
Hello.
Yes.
It's okay.
Yes.
Thank you. I'm Senthil Kumar Parimalanathan. I work with Professor Pierre Collinet from Transfer Interface and Processes Laboratory at Université Libre de Bruxelles, Belgium. Today I will be presenting a talk for all these authors and people whose name is not here as well. They formed the science team of the drop evaporation module, which is due to go to International Space Station somewhere in 2 years, I suppose so, if everything goes well. The introduction: the drop evaporation module will be placed in the EDR2 in the part which is part of the heat transfer host 2. What's exactly in this particular module is that we are trying to study droplet evaporation, specifically the fundamentals of droplet evaporation. As you know, for the technology to progress, we have to invest a lot of time in understanding the basic scientific physics or scientific principles. So one such principle or one such dynamics that ESA wanted to understand was evaporation and condensation. The condensation part will come later, which will be presented by Andre, and I would be presenting the evaporation part. So what are we actually testing is that we are testing the evaporation dynamics of sessile drop. So you have a flat plate, you put a drop of liquid on it, we call it as a sessile drop. Why is it very important than a perfectly hanging drop or other kind of droplets, which you may be familiar of? Because it involves a vapor phase where the liquid is converted into gas in an interface, at the interface. And second important is interaction with the solid, how it interacts with the substrate on which it's resting on. And of course, here what is important is to see the triple point where you have the contact line and it makes it at a particular angle. And this angle is quite important because if it's too small, it's good for certain application, and if it's too large, it's also good for other applications, which I will illustrate in the next slide. And the third one are instabilities. As Robin has described about different Marangoni instabilities. We are also interested in Marangoni instability. These instabilities occurs basically because of the temperature gradients that are induced because of the evaporation of this liquid. So we are more interested in volatile liquids, specifically as most of you have involved in space application. You know that HFE, hydrofluoroether, is one of the common liquid because of its very specific properties. So we use HFE 7100 as a working fluid for most of our experiments, and because of the evaporation you induce a temperature gradient which induces which would result in a surface tension gradient, and because of this surface tension gradient, difference of surface tension near the contact line, the triple point, and towards the apex, you have a flow that goes and there is circulation, and these circulations can also be visualized, which we will see, and there are different teams also involved in this particular project. So as you see, droplet evaporation is a multidisciplinary field where we study, especially in sessile droplet evaporation, we study fluids as well as the properties of the substrates. So as I illustrated, the contact angle is important. For instance, it could be super hydrophilic for anybody who uses cosmetics. They should stick, the liquid has to stick to your skin, otherwise it's not going to have any use at all. So the contact angle also matters, and the evaporation, the dynamics of the evaporation, the Marangoni flow, all these things can influence the contact angle as well. So this is a very nice slide which is illustrating all the application of the droplets, specifically sessile droplets. I should thank David Bruton from Aix-Marseille University. He said it would be a nice slide to show. So what are the basic objective of this particular study, specifically the heat transfer, the drop evaporation module in the heat transfer host 2. So we are studying evaporation of the sessile droplets under microgravity condition. The ground conditions would be the reference case. We try to measure the heat and mass transfer under controlled pressure and temperature conditions. Then they explore the evaporation. Okay, here an additional part is that we also study the influence of external electrical field on these dielectric fluids, HFE. Then to study the dynamics, fluid flow dynamics and the instabilities inside the drop. The instability specifically because of the surface tension gradient, the Marangoni convection, basically. And then where I play a major role is, or our team from TIPS play a major role, is the evaluating the concentration field in the vapor phase of above the evaporating sessile droplet. So the key measurements of this particular module will be to study just the volume change, take a series of pictures from the side view and see how the volume changes, from which you can estimate the evaporation rate. And then to measure the vapor cloud behavior, so we use laser interferometry in order to see how the vapor cloud, not exactly the concentration field because it's a bit tricky to estimate exactly the concentration field, but rather find out something called, which we have published a lot and we have emphasized on, studying the wrapped phase images instead of the direct concentration plots. And from the wrap phase images, which are basically iso concentration lines, pseudo iso concentration lines, so we can see these lines and see how the deformation of the vapor cloud happens in gravity and in microgravity. And the third part would be to study the influence of the electrical field on the droplet shapes. And the last part would be the instabilities, which we use an infrared camera which captures the temperature gradients qualitatively and quantitatively, and we can see these beautiful structures that is coming because of the Marangoni convection. So this is a simple model configuration. So we have the main measurement which is outside, where we have the interferometric setup, and then we have an IR camera and the infrared camera. Both so the laser just passes through the droplet in that direction, while that of infrared radiation infrared camera is focused from the top. So this is the chamber which I was talking about. It's a hermetically sealed chamber. The pressure and the temperature can be perfectly maintained. As we know, the uncertainty, what we expected as given in ESR is plus or minus 0.5 degrees centigrade. It's I know it's not so very easy to maintain, but still we are moving towards that point. And so this is the blow up view of that particular portion, where you have the sessile drop which is injected from the bottom. You have the substrate, a very special substrate with grooves, because the droplets cannot move on the substrate. This creates problem for a lot of things. So we have special grooves to pin the droplet in place, and you have heating device at the bottom which we can precondition. We can heat it to whatever temperature we need, and of course the electrode at the top. So it's not hanging at the top. Of course we have some kind of support for that. I didn't want to show that because it looks like two walls. So this is the setup. This is the simplest setup which the drop evaporation consists of. In order to progress, we had two campaigns already organized at the Red Wire, former Kinetic, in Belgium in 2018 and 2022. These are some kinds of images that we took. So just to look at the scale, so you could see this is the box which goes into the EDR, the host facility, and and here you can see the electrode. You have the droplet, the substrate, and the droplet will be injected there. And here the measuring device, the IR camera, and this is the camera for the interferometer. So all was in Red Wire. They have the copyright for this. So as you know, for the preparation phase, before going into the module, sending the module, we wanted to do some kind of preliminary experiments. And we were a part of two sounding rocket campaigns, which was coordinated by Carla Yario, who's here. We had plenty of beautiful results, which always prove. The only problem is that we have just 5 minutes. This 5 minutes was not sufficient to test all the parameters that was really needed to be tested. That's the problem with sounding rocket, the time constraint. This has been published. So you could already see that without electrical field, we have the Marangoni jet. Because there is a liquid motion which is creating this kind of a bubble inside, this bubble drags the vapor along with it, and this creates something which we called as the Marangoni jet. And in the presence of an electric field, a static electric field, you have some kind of an electroconvection where this particular vapor cloud is being totally suppressed. So electrical field, in fact, affects the evaporation rates and even the dynamics inside the drop. This is from Professor Breton's paper in Nature Microgravity, where you can see the instantaneous temperature measurements from the IR camera with and without electrical field. And here again the vapor cloud measurements, which is yet to be published. So here you can see without my electrical field and with electrical field how the vapor cloud itself is getting influenced. Of course, everything has some kind of theoretical and numerical approach. When you have good experiments, it's always nice to have a model so that we will gradually get rid of experiments, not completely, but gradually. So here are some kind of simulations that we performed for Sounding Rocket 1 experiments, ALS-1. And you could, of course, get a very similar phase-wrapped images from the interferometry, and from there you can also get very easily the concentration plots. And the second part was several people have gone for several parabolic flights, but as I'm presenting, I would just emphasize on the parabolic flights that I went. So this is a setup which is very similar to very analogous to what is going into the heat transfer host 2, but of course we have real optical table with real mirrors, and all the beam splitters which are arranged in the Mach-Zehnders arrangement. And of course we try to simulate the same thing that has been done in a small chamber with substrate, with injection, with thermocouples and all the stuff. So the parabolic flights, coming to parabolic flights also have problem, the G jitters. You will see that what could G jitter do to the vapor cloud, an ideal vapor cloud. And I would go one by one, but very quickly about the different measuring techniques or different interesting points on this module. The effect of electrical field is mostly investigated by Professor Paolo Di Marco at University of Pisa. Sorry. And here they study the effect of the electrostatic field, and you see when it exceeds certain voltage, you create this kind of a Taylor cone. These are the experimental results that they obtained from parabolic flights. And of course they have went for 2 parabolic flights, and along with Professor Anthony Robinson at Trinity College Dublin, they have been focusing on water droplets, of course, and also they have been doing experiments with not with HFE but with FC72 and ethanol. I'm not sure whether they have done it with HFE. I'm sorry. And they were part of the sounding rockets campaigns too. And Professor David Bruton's group, they specifically investigate the instabilities, as I have already told. So they put an IR camera and see what are the patterns that appears in the within the drop, within the liquid phase of the drop, and also they have done it with and without electrical field. How these instabilities could be affected. And last that I would describe, this is our work from TIPS lab, that we have studied how the vapor cloud itself is affected. So we were looking for an ideal Marangoni jet kind of a vapor field that everyone would expect as in the sounding rocket, but unfortunately the G jitter is strong enough that it affects the vapor cloud, and the vapor cloud starts dancing exactly in phase with the jitters in the Z direction. So finally, to put all together, we are in the starting phase of developing a very sophisticated numerical model, especially to study the vapor cloud and other basic instabilities inside the drop. So far we have been successful for the meniscus problems, but we are having little troubles with the droplet problems, even though we have already published all's results, which had a fantastic kind of validation. When it comes to G jitter, it's a bit complicated, so we are working on it, and it will be published soon. And we are also interested in nano coated substrates. Now we have just platinum coated substrates. We would with Crest. We are also involved in studying how the wetting behavior could be affected by these kind of substrates. So all in all, we have done sounding rocket campaigns, we have done parabolic flights, but everything has problems. Sounding rockets campaign, we have 6 minutes, we have to do all the parametric study, which is impossible for doing all the experiments. And parabolic flight, we have G jitters. It's impossible to remove G jitters in parabolic flight, and it is affecting the evaporation rate as well as the vapor cloud behavior, and in turn the instabilities also. So I propose that unless we do these experiments in the International Space Station, it's going to be really impossible to come up with some idealistic model or the numerical model which can be very realistic. So that would be the take-home message. So I would like to thank all my colleagues from in different university, and of course Redwire, the Swedish Space Corp, and the Lambda X for their part that they played in the development of the evaporation, the drop evaporation module itself. These are the recent publication. So we're just going to submit one in Nature Microgravity, which is related to the dancing vapor cloud. I hope it will be done in this month or the next month. Thank you.
Thank you, Santil. So, are there any questions from the audience? I look at Vincent.
Yes.
Thank you. Okay, yes. No, because very nice.
Okay, very nice comprehensive talk you provided. I just wonder about this vapor concentration measurement that you have. Looking at your pictures, were you able to see or detect any differences in these fringes that you have in here, in telling you as I understand it, the concentration that you're...
Pseudo isoconcentration. They are not exactly isoconcentration lines.
Okay.
They are very close to the isoconcentration lines,
right?
But they are a little bit different.
So would you be able to distinguish the evaporation rate from your surface area droplet? No.
Okay. No. The evaporation rates, we have the side view images. That's the only way we can really find out.
So you will not be able to know the distribution of how...
So that's the reason why we just ideally... So the problem is that you need boundary conditions for concentration plots to resolve. So we know the interface, which we are not so very sure about what is the exact boundary condition at the interface. Or you need to have a very large domain where the concentration goes to nearly zero. But here we have a restricted window size. So the concentration never goes to zero on the edges of the window. So inverting, which is the Abel's transform in an axisymmetric form with appropriate boundary conditions, becomes very complicated because we don't know the boundary conditions. So what we do is basically compare the vapor, the phase wrapped image, because when you do simulations, we can have the vapor cloud, vapor wrapped images, which is here. Once you match them both, then you can take the numerical simulations and get the concentration from there. That's the only way which we can get the exact concentration distribution.
Yeah, not to belabor the point, but when you're doing this simulation, you're taking this sort of electrostatic analogy.
Yes.
Right. And that is kind of mathematically forcing this distribution to be in there. I'm just wondering, this is the question that sort of bothered me for a little while in terms of cause and effect.
I don't know about how they model I should maybe I should ask Professor Paolo Di Marco, because his group is more involved. I'm more involved in the vapor interferometry. So that's the backlog, that we cannot exactly get the concentration profiles, but rather we can get only this kind of shape of the vapor cloud, how it changes with and without electrical field, and in gravity and without gravity.
Okay, no problem.
Thank you.
I just wonder how you do the interferometry, because you are a specialist. Do you count the fringes? So
no.
Oh, you measure the distance between?
That's what. You just take the wrapped images from the Fourier plane. So you convert the fringes into, apply a 2D Fourier transform.
Yes.
Extract only the important frequency that is necessary for you, and then just do an inverse Fourier transform. We already get this, get these wrapped images. But for the experiments of Marangoni in films, there we do that. So we have these images. We go a step ahead, because there we can easily estimate the concentration profiles. So there we have taken the concentration profiles, and the evaporation rates were estimated from the concentration profiles for Marangoni in films, because we know exact boundary conditions at the interface. But here, with a drop, it's not possible.
Okay, so you measure only gradients.
Only gradients, yes. So we can do an inverse Fourier transform and do an Abel's transform. We get some gradients, but these gradients are not concentration gradients, unless we know exactly what are the boundary conditions. So we have a very restricted size. We cannot apply any boundary conditions.
So only qualitative
It is qualitative,
picture,
yes. Only the shapes.
So it's because you have both temperature and concentration, so you cannot decouple them, right?
Yes, that's also important, but also the boundary conditions. We need at least one boundary conditions to start with. Sorry.
Yeah, but what you measure is the gradient of the refraction index, right?
Yes, yeah.
So, but the refraction index depends
Is
on
a
both
parameter of concentration
and
and temperature.
Okay.
But still, we have done quite a lot of analysis that the temperature induced refractive index is very smaller compared to the solutal induced refractive index. These analyses have been done, but even though having all these parameters in hand, we still lack a boundary condition. So we need at least one boundary condition to start with to extrapolate the data, because when you transfer, you get a gradient, perfect gradient, but you need to know some point, some specific line or a point where you need to know the exact boundary values. So to start. Yes. Yes, yes, this is correct, but this is what we are searching for, because it's HFE. That's the main problem. So hydrofluoroether. So we need something like that, a device that can tell us about these things. So.
Yes, I also have a question. You show at the beginning your setup where you have an nice infrared camera on the top.
Yeah.
But
this is not my setup, it's setup of Redwire.
Right.
Okay.
Right. Because I was then expecting a nice IR image, but
yes, but there are some images, infrared
top,
images, but it's not my images, but you could see from the paper which has been published, but it's not the same IR camera. This is IR images.
I got that. I got that, but it was a different study, so this is why I was wondering if you have IR images.
No, I am not working with IR images as well.
All right.
Because it's Professor David Bruton's group that is. So that's the thing. It's three complicated setups are in this drop evaporation modules. They all have separate coordinators who are handling these experiments, and they are expert in their own field. So that's why it becomes such a multidisciplinary and a very very exhaustive kind of setup. Very ambitious, but as somebody said yesterday, Europeans always have a very high ambition to start with, and they create the benchmark for everybody. So obviously this is one of the benchmark experiments, but if it flies through, the amount of data and the amount of results and the amount of output is going to be tremendous. Our colleagues from other space station has also did such experiments. I don't know how successful were there, but we have so much of extraordinary and beautiful results that can result from this particular drop evaporation module. So I hope it flies. Thank you. Any questions? Okay.
I have another question.
Yeah.
Concerning this video, maybe you can help me with the physics, because we did the electric field experiments in pool boiling.
Yeah.
With electric field, also with Polo. And I understood that when you have the electric field, you have the different dielectric properties and you have a force on the interface. But if you have maybe just a small amount of HFE or FC72 in the vapor, what is the physical effect that is moving the vapor?
Okay. So you're saying why there's some kind of growth? You mean the way that it's
because I would assume that the properties of let's say pure nitrogen and nitrogen with a bit of FC72 or HFE molecules are not so significantly different than, for example, comparing the vapor to the liquid phase.
Okay.
So what is the physical force that your vapor cloud is moving completely different within the electric field? Is it maybe also the shape of the droplet that it's pushing the vapor to a different direction, or it's really in the vapor?
It's the liquid itself is convecting. You have electroconvection within the liquid.
And that's the liquid.
Yes, is the one which is dragging the vapor, because you have the coupling between the liquid and the gas phase.
So it's
yes,
more on the liquid.
Yes, more on the liquid.
And the vapor phase is a result of that.
Yes,
okay.
Yes,
understood.
Exactly.
Yeah.
So exactly like the Marangoni. So the Marangoni convection pulls the vapor with it, creating the jet.
Okay, thanks.
Okay, let's thank again our speaker. And now we move to the next one, Andrei Glushchuk. I hope I pronounced it well. From the Microgravity Research Center at the
from Crest.
Crest, sorry.
Now it's Crest.
Université Libre de Bruxelles.
Hello? Sorry? It's important. So okay, I'm going to present another space experiment. It's called condensational fin. As you noticed, there are a lot of experiments which generate vapor. And the target of this experiment is to do opposite, to convert vapor to liquid, finally, from all experiments. How to switch slides? So, as you know, there are a lot of different designs of condensers, which provides which satisfy different criteria, like compact, size, efficiency, some ranges of applicability, and so on and so on. And one of the widespread techniques to have efficient, in some way, condenser is to use 3D complicated surface. Oh, sorry. Why? Sorry. Sorry, I showed you almost everything. Okay. One of the way to satisfy different criteria is to use 3D complicated surfaces to reach criteria of compact, criteria of efficiency, and so on. And the enhancement is caused not only by the surface itself, because when you have complicated surface, you increase contact between vapor and metal, but also thanks to surface tension effect, because at some scales, surface tension redistribute liquid and helps to promote condensation. There are a lot of propositions of this surface, like simple one is a rectangular, trapezoidal, up to some 3D shapes and even optimized shapes, but most of them has a size around 1/3 millimeter, quite small, and this scale is caused by the limitation of capillary force. In our way, on ground, the main competitor of this force is gravity, of course. But at small scale, capillary force is dominant and helps to promote condensation. And here we come to concept of the experiment itself, because one way to see how capillary forces affect on condensation is on ground is to make a small object and try to measure. But if gravity is removed, it is possible to make our object as big as we want, because there is no more main competitor. There are several numbers used to describe ratio between gravity and capillary forces. It's a bond number showing Dirichlet ratio, but the most interesting is capillary constant, showing the scale where both forces are equal. And as this table shows some estimations, and as you can see here, the size, the scale when both forces are equal is few millimeters. But if we reduce gravity, let's say 10, 20 times, it's already measurable in terms of millimeters, 10, 5 millimeters. And this object could be created accurately and could be analyzed. So, idea of the experiment is to simplify measurements and by using microgravity and using different ways to get it. So finally, the concept of experiment is to take quite a large object to create a very good to create good conditions to have condensation, to measure as we can do using available techniques, because the scale is enough to use widespread techniques for thickness, temperature, power measurements, and because of the size, it is possible to see effect of temperature, of material, of topology, of coating, whatever we want, because again, object is quite big. To realize this concept, two questions should be answered. First, which object? What should be the shape of the object and how to create conditions? So, now, coming to the first questions, it's about the shape. During several campaigns in microgravity, we tested different shapes, different size, to see what could happen, because the shape should provide stable flow of condensate. And as we mentioned, noticed, you can see on this video. Oh, sorry, why it doesn't work? Okay. So some shapes can provide stable condensate flow, and you can see the strong effect of capillary pressure gradient, but at the same time it is sensitive to external forces or jitters or whatever. Some shapes provide very sensitive film, other shapes provide quite strong film, but very thin film. So we did several campaigns, and at the end we decided to simply take a shape which provide a constant gradient of capillary pressure without any complication. So this shape should provide a constant force, stable flow, and strong enough to sustain any vibrations or other forces. Concerning a second question is how to create condition, because vapor space should be created and the stable retraction of liquid should be organized. And here the idea of experiment is to put both element, evaporator and condenser, and as much as possible element inside the same volume. In this case, vapor will be easily generated and can freely flow to the area of condenser and will be converted to liquid. Several optical techniques should be used to make measurements of film thickness, of vapor around the condenser, to see how liquid is distributed after condensation. Concept is simple, but technically it should be realized. So we did several flights to prove the feasibility of this system to work, first of all, and to find appropriate components, because even evaporator or other components should not be sensitive to vibration and other external forces. So we did several flights using the thin which provides constant capillary gradient. Of course, thanks to all tests, results, and reports sent to ESA, the elegant first prototype of space experiment have been developed with all measurements techniques and all visualization capabilities. Unfortunately, everything is placed inside almost closed box except several windows, but still it was working well and it was nice to play with this because all components was on the table. Next step was a second prototype, considering results of our scientific experiments and results of first prototype test. Second prototype was created. It's still first one. Second prototype was created, but this time it is completely closed and integrated inside heat transfer host 2. This is a setup providing all communication, measurements, techniques, data acquisition, everything, and ready. This is a prototype of a system which will be sent to ISS. This time there was less possibility to play with this, but we test all system. There was some comments which provided to ESA, but it worked very well. So here you can see how it is look. How does it looks like? The shadow of the fin, it's provided by one of the measurement techniques, and how it looks like from the top visualization. And next step is space station. So, I mean, nothing to say, because only microgravity condition could give us valuable, accurate measurements. Thank you for your attention.
Any question from the audience? Okay.
Thank you very much. Just two small questions. The first one, I didn't understand the purpose of the two needles you have on the bottom. It's if just okay.
As I mentioned before, it is important to create a good boundary condition. It's not only to promote condensation, but also to make accurate measurements. And as you know, during a condensation, as during evaporation, there is a thermal expansion effect. And if condenser consists of different materials, as in our case, the object can dilatate, can move. And of course, it will affect on the measurements. An idea to put some reference optical objects which has very low thermal expansion effect. And they were.
Okay, thank you very much. And just other question is...
sorry to interrupt you, just to prove what during experiments we measured movement of our object within 100 micron. But thickness measured is 60 micron. So imagine what they're comparable, and of course it should be taken into account.
Okay, thank you.
Please, second question.
Second question is what is the material for the foam that takes?
This is aluminum foam.
Aluminium, and didn't you have some? Of course, I guess you took into account, but about thermal conduction for having also condensation on the foam also, or on the needles.
No, good. You're right. Yes, we consider it, but the foam does not affect. So effect of the foam is around several percent.
Yeah,
of the overall condensation.
But it doesn't affect the condensation on the...
No, not at all.
Okay. Thank you very much.
It works like as absorber of condensate after. Questions?
No. May I ask you a naive question, maybe, because I didn't get it. Can you explain me a bit better about the temperature measurements? I didn't get the Finnish sensorized things.
No, I didn't specify. Temperature measurement where, actually?
Yeah, that was my question. I didn't get if, I mean, you measure the temperature around the fin.
So there are, as you know, temperature is one of the way to describe heat transfer process. And the temperature of vapor will be measured optically, and temperature distribution inside the condenser will be measured using several sensors inside. They are shown here. I hope, yeah. And the temperature of the surface will be reconstructed after.
Okay. Thank you. So, there are other questions? Okay, let's thank again our speaker. And we move to the next one, Mihai Boni from the National Laboratory of Laser in Bucharest. I said well this time, more or less. Okay, it's an improvement. Okay, so the floor is yours, Mihai.
Thank you very much. So, 5 years of work in 29 slides. This is the story of DropCall, an instrument for studying drop coalescence in microgravity. Our aim is to study droplet coalescence, binary droplet coalescence, and mixing of different liquids in microgravity. And this is really important in the context of human space exploration, especially for the drug formulation and drug delivery in long-term missions. We've done a lot of preliminary terrestrial experiments and here we can see two of them, the coalescence of two droplets of water on the top, and the coalescence of two droplets of water and ethanol on the bottom. You may see that gravity is affecting the liquid bridge. Of course, it's affecting also the shape of the droplets, of the initial droplets. Here we are using the diameters of 2 millimeters for each droplet. Why 2 millimeters? Because if we go higher, the droplet will fall from the needles. So this is why we need microgravity in order to be able to generate larger droplets, spherical droplets, in order to first of all to simulate, and usually in the simulations you are using spherical droplets. Also, you may see that the mixing is different. Of course, in the case of water and ethanol, we have the gradient of surface tension, and Marangoni flows arise. In our experiments, we will generate, as I already said, different volumes of droplets, so different diameters. One droplet will stay in place, and the other one will be moved at different velocities. After coalescence is detected, the camera will start to record. We are recording 500 milliseconds prior the coalescence and 500 milliseconds after coalescence at a higher frame rate, and after that the frame rate decreases automatically, and we are recording another 5 seconds at 2000 frames per second, so a lower frame rate. In the case of coalescence, we are using 8000 frames per second. Of course, after coalescence, there is a protocol that removes the droplets. The liquid is sucked by those two needles, and it's applied protocol that is rinsing the needles. And why is this really important? Well, we want to have all the time the same conditions, experimental conditions. Let's meet the drop call science team. The science team coordinating unit is the National Institute for Laser Plasma and Radiation Physics from Romania, and our partners are the Technical University of Darmstadt, Germany, and Carnegie Mellon University from the United States of America. And our ESA science coordinator is Dr. Sebastian Vincent Bonion. In this international partnership, we developed the experimental scientific requirements, which are the framework for the device, for the building of the device, entitled Setup for Investigation of Drop Coalescence in View of Medical Applications. And as an overview of our experiments, we will have 6 months. Right now, I could say 5 months, because the commissioning phase already started for 2 weeks. So we will have around 5 months of experiments on board the International Space Station, 70 different types of experiments. We are applying 8 runs for statistical purposes. This will give us 560 runs, so a lot of data. We are using 7 velocities from 0.01 millimeter per second up to 10 millimeters per second for diameters of droplets with volumes between 4 and 65 microliters. 2 solutions with different, 2 liquids with different surface tensions, water and ethanol 10%. Why 10%? Because this was the maximum concentration that we were allowed to send on the ISS. We are the guys that send alcohol to the astronauts. The coalescence will be recorded at 8000 frames per second, and as I said, the mixing will be recorded at the maximum velocity, the maximum frame rate of 2000 frames per second. For this, for all the data that we are acquiring, we have 4 terabytes, 2 hard drives that will come back on Earth. The device will be thrown away in space at the end of the mission. And also we have the possibility of exploring new types of experiments at the end of the mission, like the bridge rupture experiments. And you may see why we are doing this at the end of the mission, because we can generate secondary droplets that may flow inside the interaction chamber, and they could be a showstopper if we will try to run this kind of experiments from the beginning of the mission. From an experimental concept to a functional payload, we, the science team, made the requirements, and we've designed a sketch of the experimental setup, and from that sketch, the Romanian in space engineering, the payload developer, has built a functional payload on behalf of ESA. This is a cube of 10 by 10 by 40 centimeters that has been installed in the IceCubes facility on the Columbus module on the ISS. This is the exploded view, and I can explain what are the main components of the device. So we have the image acquisition system. Everything except of the camera, it's custom made, even the lenses. Then we have the interaction chamber. There we have a sledge with some valves and 2 needles. The LED that is illuminating the scene, and also a lot of sensors of temperature, pressure, and humidity. We don't have pressure. We don't have sensors of ethanol. We didn't. We were not let to put any sensor of ethanol, because usually those sensors are heating. They have some parts that are heated, and they said no, stop. And at the back of the device here, we may see the pumps and reservoirs bay. We have 2 locks from a safety point of view. In each lock, there is inserted nitrogen, and the liquids were degassed. This is the core of the setup, where we can see the valves, the needles, and we have 2 motors. As I said at the beginning, we can do experiments, or the matrix of experiments right now, it's designed to keep one droplet on the same place and to move the other one, but we have the possibility to move both droplets at a certain time. And in order to develop the needles, because again, the design of the needles needed to be worked in such a way that the droplets will not detach during the experiment. And again, this would be a game stopper for us if some droplets will start and float. I think it will be a really nice video to have with droplets floating, but not in the case of science. So we went in the 79 parabolic flight in October 2022. Here is the team, 4 Germans and 1 Romanian. This is the largest Zarges box that my colleagues from Darmstadt, from TU Darmstadt, could buy from the market. And why the largest one? Because it has 2 experiments in the same box. This one was the DLR experiment, which is related to the ISS experiment, and on the top here you may see the ESA experiment, where we tested 8 needles with different geometries of the tip, with different coatings, with different outer diameters, inner diameters, with the working fluids that we are using on the ISS. And this is what we were recording. We were pumping a large volume in order to obtain a 7 millimeter diameter. And we were looking for the moment when the droplet was detaching from the needles. As also the other colleagues said previous, the G-jitter is quite high, and you may see how the droplets are oscillating during the microgravity phase. And I understood that a lot of you here are veterans in the parabolic flight, but for those who never saw a parabola inside of a plane, I put this video here. So we were 2 operators and a spare. As you know, the scopolamine that we are taking in the morning, it's hitting really hard for the first time. This is the 1.8 G. All the experiments were, the setups were automated, only push of a button. Okay, so during the entire preparation of the mission, we've done a lot of tests in Romania and in Germany, in different laboratories, and we tried to help the payload developer. For example, in our case, we made a lot of measurements of surface tension measurements for the chemical compatibility test for the IV bags that they are using. Since we have ethanol, we were measuring twice per month the surface tension of ethanol extracted from those bags in order to see if the surface tension is increasing, this showing if the bag have a high permeability, or if the surface tension is decreasing in the case of water, showing that some polymers are migrating into the water and are decreasing the surface tension. We also made a lot of tests for the needles. There were 2 different designs made, one by the science team and another one by the payload developer. And also we've helped them, so we made the characterization, the optical characterization for the needles, and we made the chemical compatibility of the coatings and the anti-fog coatings. Yeah, a lot of work has been done. Also, in the same time, the payload developer has tested the device. Here they were, on the first picture, they were at the ice cube center, and they were testing if the cube is fitting inside the ice cubes, and also they communicated with in the same way as it happens right now on the ISS. They even played roles. Someone was from the ground control, the other one was from the SAS, and another one on the laboratory. They made also tests of electromagnetic field and vibrational. Let's think about that there we have a lot of optics, and during the launch of the rocket there are a lot of vibrations. The science validation came, and there were made a serial of videos recording the coalescence and the mixing. In this case, they used only water since there were only tests. And as the science team, we verified in all these videos if our requirements were achieved. We also made some other kind of measurements. And on 4th of November, so this month, the science team and the payload developer went in Florida to witness the launch of the SpaceX 31 and the departure of our baby, let's say, from ground to the ISS. Here you may see some part of the science team, and here some part of the science team and from the payload developer. And let's watch for 1 minute the launch. There were a lot of teams that had payloads on the Dragon capsule. So everyone was really, really excited that their work will gonna reach ISS. Okay. So our payload was mounted by the astronaut Don Petit something like 2 weeks ago in the IceCube facility. From then, the commissioning phase started. It is the engineering phase right now. From the next week, we will have the science commissioning. The device was mounted here. This is Cube 17 next to Cube 9. Right now, we need to discuss with these guys because from what I understood, they have some human tissues there. So I think they need some higher temperature. We need a lower temperature. And when we build it and we designed this, we didn't thought that we will have a neighbor that will have they will have different needs that we have there. But for sure, we can find a common sweet spot, let's say. And you know that all the great, or almost all the great discoveries were made by mistake. Even our first droplet, it's something like Inception, a droplet in a bubble in a droplet and so on. This is the first droplet that was generated with the device. After several days of working on the device, the payload succeeded to remove almost all the air from the tubings. And yeah, they've done several, they are testing the device. And 1 hour ago, I received the first movie that has been taken with the device. Right now, they are extracting frames from the video and they are downloading. So it is not the full video. That will take something like several days to download one video, the raw video. But they are extracting images from the video and making a smaller one, let's say, and it's comprimed with an MPEG code. Okay, I will play it after. Okay, so as a future work, next year in 2025, a modified version of Dropcall will fly in the maiden flight of the next capsule. So the differences in this one is that we were allowed to increase the quantity, concentration of ethanol from 10% to 50%. But in this case, we will have only 6 experiments since it will stay in microgravity only half an hour. And at the end, I would like to thank to the ESA team for their support, making the Dropcall a success. Our science coordinator, Sebastian Vincent Bognon, the payload manager, Matteo Tacconi, the payload integration manager, Luca Facciolati, and Beth Lomax and Jan Jerome, who were with us the whole years. And also, I thank you for your attention, and I hope it was an interesting presentation.
Thanks a lot for a very didactic presentation, actually. So, any questions from the audience?
Thanks. Maybe it's a hard question because you just got the video 1 hour ago. But when you go back, do you know where the oscillations from the left droplet are coming, and do you have some air in the right droplet?
Yeah. So right now there is air. Sometimes there is air in the droplet, and this was the discussion that I had with someone in the break session. Maybe we don't know right now why air is still coming there. And one possibility, after I was watching the presentation earlier, is that the liquid could go on the walls and then can entrap some on the walls of the needle and can entrap some air there, or there is possibility that from the vibration something to be a little bit loose. Right now we don't know from where the air is coming, but it's not all the time, so it's time to time. And the oscillations, this is something that need to be investigated. We had that problem only on one velocity on the ground. For the rest of them, everything went smooth. I don't know if this is the velocity that had problems.
And another question, you mentioned that you, let's say, get rid of the fluid after an experiment to get a fresh run. How you do that? So is there another...
So what I didn't said is that the entire chamber is saturated, is fully saturated with water for the first 2 months, and after 2 months we are switching to ethanol. We are saturating the enclosure with ethanol and water. The water is already there. And then we are doing the experiments. We are sucking, so the liquid it's absorbed by the needles onto the needles, and they are the liquid goes on another way. It's a valve with a freeway valve, and the liquid is going into a large reservoir, waste reservoir. After that, with the working liquid from each needle, there are several rinses of the tip, because right here we have methylene blue in a low concentration. We have 0.005% concentration in order not to change the concentration or the surface tension of water. But let's think about when we have an experiment of ethanol and water. What will happen? You will have a lower concentration of ethanol that will be extracted through the water needle. This means you will impurify that needle. That means when you will generate the new droplet, you will generate a droplet that is has lower surface tension. So we are applying an protocol of rinsing, which was developed on the ground. And another question that came later is that, okay, we are washing it, but we are generating water in ethanol vapors. So the vapors are migrating to the interface of the droplet of water. So for sure, the surface tension will be decreased. This is the reason that we are doing the experiments in 1 minute. And on the ground, we saw that, okay, we don't have the same conditions, but on the ground, we've seen that after 5 minutes, the new concentration in the droplet is something around like 3% ethanol. What is really interesting here is that the vapors of ethanol and water, they will create a layer around the droplets. And we have to think about that experiment with the flame from a candle that on the ground has the shape of the flame, and on the ISS it's like a sphere. This is really interesting to see how that gap of vapors are influencing the coalescence.
Thanks.
Thank you very much. I don't know if you... Here it's water and water?
Yes.
Okay. And you answered to my first question about the influence of blue methanol on surface tension. Don't you think with time you could have a Sir concentration on the interface that could modify it with time? Or are you sure?
This is why we are rinsing, after each experiment, we are rinsing the tip.
Okay. Thank you.
With several rinsings.
And second question, but I don't remember my second question, so it will come.
Should I go back or?
No, it's okay.
Why different colors?
So in order to see the mixing of fluids. Yes, it is intended. Yeah. So. Right, I can go on the first slide, and so here we may see the. Is it? Okay, now it's working. These are made on the ground. So you may see how the fluids are mixing by inserting their dye. In this case, we chose methylene blue because we are studying. This is a study for medical applications, so we are using water, ethanol, and methylene blue that can be used further in other missions. The dye? No, it was chosen. So the concentration, it was chosen in such way that it doesn't change the surface tension of water. But what we observe is that even by that we may see in the sedimentation on the ground. Right now, I'm not sure if it's from the because there is methylene blue or there are other mechanisms that are doing that. But in the last movie that I show, this is totally opposite. Sorry, I didn't. But I don't know that. We didn't study that. But we are trying to have as much as possible to have no gradient or to reduce the temperature gradient inside. And for this, we mounted 3 temperature sensors on different places to visualize, to monitor the temperature gradients on time.
I just wonder what can be the reason of symmetry breaking, because you do have the symmetry breaking in space. So what breaks the symmetry? Do you have any idea? Because it should be symmetric,
so
but it's
yeah.
not.
But there are also some. It depends also how symmetrical the needles are, the diameter of the needles, since they were mechanically machined. This could be a reason.
Too strong. I mean, the needles are too far. It breaks immediately, so it's hardly.
And also depends on how if the droplets have the same volume. Because right now I cannot tell you from this if they use the same volume for the experiments, and you will see by changing the volumes that.
Yeah. Okay. My guess would be I wondered from the beginning why you use water, because the water is a very nasty fluid, the nastiest of all. All the contamination that you have inside will go to the surface and will modify the surface parameters, maybe not surface tension, but its evaporation properties and its dynamic properties. So you have probably the gradients of these properties over the surface, which causes this effect. I mean, that would be my guess. In this case, for instance, for ethanol, ethanol would have less effect than this one. And if you don't use water, I mean, because in ethanol you always have water, so it's always also the bad, example. But if you use some non-ionic, liquid like methanol, for instance, or any other acetone, whatever, you won't have this problem. Why did you use water? I mean, what?
As I already told you, that there are medical applications behind this. There are other experiments that were done prior, because in our group we are studying medicines and laser interaction with medicines, and the prior experiments from where the experience came and this project came. In those we were studying medicines irradiating, for example, in a drop tower. In those 5 seconds, the medicines were irradiated, and we were changing their surface tension due to the photoproducts that were appearing, and they were photoactive and tensioactive photoproducts. And this is the reason that came. So we had previous experience with water, testing on water and medicines. So this presented interest for ESA, and this is why we chose water and ethanol. And regarding some contamination, there were applied a lot of methods of washing the entire system, and the system was, it's not perfect. Nothing is perfect. But also we've done the sterilization of the device in order to reduce the probability of something to live in there and to create something like biofilm, and to decrease the surface tension of water.
I have one more just. You show that you slow down your movies a lot of time.
So they right now there are only frames grabbed by and downloaded in order to have a video. The videos are recorded at 8,000 frames per second, so we will have really slow down. And yes, it's not 100 frames per second, but we have to take into account what field of view we have there, because we want to look on large droplets of 5 millimeters in diameter or even larger, and we want to record also the mixing. So if you just make a region of interest really small, then you can go, and also you have to take into account the space for the camera, the amount of space, physical.
In fact, I didn't ask my question yet. Sorry. No, in fact, just the time you show is real time, not the real frame per second, but it's a real time here.
It is 50 frames per second from what I remember when I downloaded it.
Is it slow down?
It is not slowed down.
Yeah, okay. Sorry, okay. No, so my question was because I thought it was very violent motion, and did you observe not for water but other fluids some kind of splashing effect, some kind of emission? No, okay.
No, not at the velocities that we are using.
Yeah, okay. But in fact, it's not slow down.
Yeah.
So I understand better. Thank you.
And
I think the bubble, which is you're seeing, is actually entrapped at the interface and is being pushed there. Maybe if you see a high-speed image, you could see that the bubble is been entrapped in the middle and it's been pushed there.
Yeah.
Because this kind of thing we have seen in our experiments also, that the bubble getting entrapped from the liquid because of the microgravity and pushing it down, the bubble being pushing it down. So
there is a
Yes, so that also could lead to this kind of asymmetry. Isn't
Yeah,
it?
that could be a reason. And we can remove that bubble from there, but there should be applied several cycles of withdrawing liquid from there. And the idea is that there are piezo pumps. And you need, when you have air in there, you need to apply different parameters like the frequency and also the voltage. And if you have liquid, if you have water, you have to apply. So somehow they have to play to tune those parameters in order to remove that air from there.
Just the last question. Is there a surface tension difference when you mix it with methylene blue?
Really, really low. It's
really
like something like 0.5 millinewtons per meter.
Okay. All right. Thank you.
Okay. Let's thank again our speaker. And yeah, we have just a few minutes left. Even if not true.
Just I wanted to answer Axel's, because on live people have seen, and it's the electrical dielectric permittivity in the gas, not in the liquid. I wanted to correct my answer for that. And for the boundary condition, as I was talking about the Abel's transform, the constraints from the Abel's transform, the inverse Abel's transform, to the lack of integration. We don't have a wide window, but we have only a shorter window. So we cut short of this integration, which is wrong. So if you have a wider window or make all the vapor to force upward, so there is no vapor in the edge, then again it's possible for us to integrate and get the concentration profiles directly. So this is always the constraint coming from the window size. So we have very restricted dimensions that we can carry to space. This is the problem. Thank you.
Okay, so I think it's time to close now this session. Thank you. Somebody wants to add something? I don't know, to wrap up the discussion. Vincent? No, so okay, let's thank everyone, the speakers, the audience, and see you later, I suppose.